All right. Good afternoon, everyone. So today, if you remember last class, we finished the USDA NASS data analysis script based on mostly on looking at plots and making some maps, making some tables. So not in a geospatial way. Um, and towards the end of last class, we ran out of time, and so I decided to not show you then, but I wanted to tell you a little bit about Quarto reports. So that always I'm going to start off with that today, and then we'll get into our new exercise today, which is going to be to look into that USDA NASS data on a geospatial way. So to get started, I'm going to navigate here on my side. You can please go ahead and do that on your side as well. I'm going to go to that to the folder of our class, right? So I'm navigating to that here on my computer. And if you remember, you should be seeing something like this, where we have that 03 NASS folder. That's where we're keeping the files related to this project. If you go inside there, you're going to have that rproj icon. You're going to have some scripts. You're going to have two pieces of data there, and then that output folder. So remember that I told you, and I highly encourage you that if you're working with RStudio projects, always launch that RStudio instance by clicking on that rproj icon to make sure that all of your files are in the right place, you're seeing the right folder structure, and so on. So go ahead and launch that by clicking on the rproj of the 03 NASS folder. This is how it looks like on my side. I think it would probably look similar on yours. So first thing, we check we're in the right project, 03 NAS on the top right. So that if it says project none or something else, then you're not in the right project. Make sure you do launch from that rproj on that folder. But I'm assuming everyone has the correct project launched. I'm just gonna quickly, so this is my, for me, that USDA NASS summary partial script that you also had on your side that we developed last class. If you're not seeing that, if that did not pop up for you, can talk, or you can move around this panel here so you can see more of your files tab on the bottom right. Click on the R blue button that takes you to the home folder of this project. You can navigate to code and then just launch your QMD file from here by clicking on it. All right, so once you have it here, I'm not going to go through everything we did last time because that's in the past. We already completed that. But what I do want to come back and just revisit with you is one of our learning objectives of the previous, or of this script, which is the previous class script, was to create a high quality report. That part is what I had to skip last class because we ran out of time. So I just want to revisit that. As you remember, we developed this script here as a Quarto file. We know that because it's a .qmd file. It has this part here, the script that's called the YAML, which is basically just where we set up some information about how we want this Quarto to be rendered. So that's a new word perhaps. So we're going to render this Quarto file into a report. If you remember, we have in here outside of chunks, whenever we have £1 sign, that indicates a heading 1 level. If we have £2 signs, that indicates a heading 2 level, and so on. And then we have all of our chunks with our data information, all that, right? Assuming the next step we're going to do is to render this into a report. And this only works if you have no code issues in any of the chunks on this script, which you shouldn't have if you worked in class, developing class with us last time. You should have everything working. But let's say I have one piece of code here that has a typo. Maybe I'm saying soy 1 and that object does not exist. When rendering, each chunk is going to be run. And if that chunk does not run because this object soy 1 does not exist, then it's just going to stop rendering right there. It's not going to complete. But I am assuming you all followed along last time, so you should have working code throughout this script. And with that, if you come here on the top of the script window, there is this render button. I want to ask you to click on that. When you click on that, basically this Quarto file is being interpreted and rendered into a report. So that finished on my side. Once it finishes, it pops up here on the viewer tab, and we can take a look at that. So I'm going to click on this button just to open that on my browser so you can see what was created out of it. So all the information we had on the YAML, so that was the title, the author, and other things, they populate on top. All the heading 1 levels are appearing here. All the text that we had is appearing here. You can notice that on the script, I'm just going to toggle that here back to the script. Every time I had something highlighted, starting with 2 asterisks and ending with 2 asterisks, that text becomes bold on our report. This is a link, so an active link, and you can go back to the code to see how we created an active link. This is basically how we do it, and so on. The report itself also has a couple of things. So one of them is you're going to see that each chunk that we had is there, but it is folded. So we're not showing our code by default on the report, but the person can toggle that on and off and see the code if they want to. Right, so if you just play around, you're going to see that. So our objects, our printed tables, our summaries, and then our plots are all here on this report. And if you just go all the way down, it's just going to be everything we've done in that script all the way to the end. It's also nice because you have this interactive table of contents on the right side. If you want to navigate into different parts, you can do that. And the reason why I'm showing you this is a couple of them. So one is Quarto files. They are the scripting files we're going to be using in R. And if you develop them, keeping in mind that you could turn that into a render report, and you keep tabs with your heading 1 levels, heading 2 levels, and all that, then it becomes really easy for you to create a very professional looking report just by rendering it and perhaps sharing with somebody. Sometimes perhaps you have a colleague or maybe your advisor, they want to see what you're doing. They want to know, what did you find? How was the data? All that. You can share this with them. If they don't really care about the code, you can hide the code like we're doing here. But perhaps they do care about the code. They do want to see how you did things. And so you can include this option of, toggling the code on and off. They have that option on their side when you share with them. This HTML that was rendered, HTML is one of the file types we can render a script like this. It can also be rendered to a Word file or to a PDF file if you wish. HTML is just, I think it's nice because it opens in any browser if you share with somebody. They don't have to have R installed. They don't have to have anything installed. You're just going to share the HTML with them. And it is interactive, right? You can navigate interactively on this file here. So it's a nice way of sharing your analysis by just quickly hitting that render button and getting a product out of it very easily afterwards. The other reason why I'm showing you Quarto is because this is going to be the format you're going to submit your mini project, which we're going to talk about that later today. So that's also another reason. A couple of things that I also want to point out is if you come here in your files and you come on your code folder where this Quarto file was, you're going to notice now there is an HTML file living there. Even if you come here and show folder in your window, there is now an HTML file with the same name as your code. And that is the file you could share with anyone, and they would not have to have any software, special software to open that HTML report and still see all of your code, data, and outputs. All right, I do want to show you some quick customization of Quarto if you feel like whenever you're submitting your mini projects, if you want to play around. So here on the YAML, you see there's a lot of things we're changing. For example, code fold we're setting to true. That means that whenever it renders to HTML, we can toggle on and off the code option. We're asking for a table of contents equals true, number sections equals true. So everything, I mean, it is code, but it's very intuitive, right? And then it has this option for a theme. So the theme of the report, so not the ggplot theme, but the theme of the reports that I'm using is Cerulean. I left you a few options here that I thought were really interesting as well if you want to play around. So let's say let's try journal. So I'm just going to change that option. I'm going to click on save and render again. It's going to re-render everything with a different theme. In this case, going to be theme journal. I just want to show how that looks like. So it opens up like a different color scheme for us. It's just a little bit different. So the content's still all the same, but just the theming of your report change a little bit. I'll show you one more, which I think is very different. I believe is quartz. Let's try quartz. I'll try one more, and then if you're interested, you can try more on your side. And if not, you don't have to try either. I just wanted to show you that you have the option if you do want to customize things a little bit. But there's some here that are very different that, if you want to add some of your personality, I guess. Yeah, this one is one that's very different. So this theme here is the theme quartz, right? So anyways, I just wanted to show you about that any Quarto file. So so you all have an idea, all of my PowerPoint slides are made with Quarto. My website is made with Quarto. My script files that I analyze data are made with Quarto. So Quarto is just a very flexible file type that you can use for different things. And here I'm just showing you that you can also use Quarto to create professional looking reports from your data analysis. All right, so any questions about that? All right, I don't hear anything, so I'm gonna keep moving here. Okay, I'm gonna basically close the script as we are done with it. We're not doing anything else with it. Today, we're moving to our new script, and I'm gonna need to ask you all, just to make sure my memory is not failing me. I believe you have already moved. So the next script we're gonna be working with is 0123 NASS spatial partial. Did you already install this and download this from GitHub? Aman, do you remember doing that? Okay, so Aman did it. In Tifton, did you already have this script on your code folder?
Not yet.
Okay, so Paulie said not yet. So please go ahead and download from GitHub. So you already have the link, but it's the 2025 PPA GitHub repo. Download that repo and then move that script into this same project. So we're not creating a new project. We're just continuing to work with the same data. It's just a different script. So please go ahead and download that from GitHub as you've already done this in the past. Just if you need a refresher, I'm going to go on GitHub on my page, Leon Bastos, and then the repo is 2025 PPA, right? So if you just click on that code button and then download it, it's going to be a zip file. The code is going to be under 04 class code. It's going to be the NASS spatial partial. So please then move that script into the 03 NASS project under the code folder. That's what you want to have. I'm just going to give you a few minutes here to get that done. It should be pretty straightforward. But if you have any questions or problems or issues with that, let me know. I can help you troubleshoot. All right, I'm gonna get started. If by the time that we get coding, if anyone needs more time, let me know. Uh, but I'm gonna just get moving here so uh, we can move ahead. All right, so assuming that you got that script from GitHub and that you move that script into your 03 NASS project inside the code folder, then you can just click on that NASS spatial partial. So we're going to start working with that project, with that script, sorry. All right, so the goal of this, so if you remember, we downloaded soybean production at every county that had data reported in Georgia from 1969, I believe, to 2023. So lots of data. We exported that data set from USDA NASS. We brought that into looked into that data, how the data looked like, all different aspects of it. What were the counties with the highest production, the lowest production, a lot of different things the last time. But we did not have any spatial context, really. I mean, we did not make any maps out of that. First off, because it was just a CSV file, right? So there's really CSV files in themselves are not spatial files. But also we didn't really work with that in a geospatial sense. So this script here is going to be basically for us to explore that data set in a geospatial and temporal way as well. As you know, we already downloaded that raw data before, so it was downloaded from the USDA NASS Quick Stats portal. This is a link for that if you want. So specifically today, my learning objectives for this exercise are to import that wrangled data from USDA NASS. If you remember on the previous class, we brought in the raw data from USDA NASS and we did a lot of things. We wrangled first and then explored the data, and then exported that data set to file, the wrangled version to file, so we could use it. Today, we're going to bring back that wrangled version and start working from that with that one. So not the completely raw version, but the one that we already fixed some issues with it. We're going to connect that tabular data with spatial data based on county information. We're going to create a publication-ready static map and an interactive map as well. There's going to be interactive on that HTML Quarto report. And then we're going to explore a little bit more of that Quarto report with that interactivity. And also not listed here, but I think we're going to have enough time to really introduce the mini project, which is coming up, which is going to be all connected to what we're seeing today. All right, so here's something that I want you to think with me and to realize. So the data set that we have up until this point, again, is not geospatial in nature, right? However, we do have the county names, right? So we have county names in that data set, and we can use that information to connect that data set to geospatial shapefile that has county names and the actual polygon of each one of those counties in Georgia. There are many ways of obtaining these types of shapefiles in R. I'm going to show you one of them, which is going to be through this package called USA Boundaries. So this package, it's easier if you try to install it directly from GitHub, so not from CRAN, not just using install.packages. So what we're going to do first here, I want you to come to this chunk, remove that pound symbol from the install packages remotes. So first step we're going to do, and then just run that line of code. So do not run the whole chunk yet. Just that line of code, install the remotes on your computers. This package remotes here is going to help us to then use functions from that package to install other packages outside of CRAN. So once you install this package called remotes, again, you can either comment that off or just delete that line of code altogether, up to you. Because we are only installing once, and then you can come here on the next line of code. So here, if you just uncomment that, this is basically, if you remember that syntax of function name and then colon package name, this is just saying we want to use the function install GitHub from the package remotes, and then here we're giving the GitHub path to that. So basically, our open site is the GitHub user, USA boundaries is the repo inside of that GitHub user profile. So go ahead and run this line of code first, install the USA boundaries. I'm not going to run on my side because I've done this already. But if you have if it gives you issues or warnings or something that doesn't seem like it's working, let me know. Once that installs, you again want to comment this off and then remove the # from the next line of code. We're going to install another package from GitHub called USA boundaries data. So go ahead and install that as well. Once that goes through, you add that the hashtag symbol in front of it again. And then after that, we're going to be installing two other packages. One of them is called MapView. MapView basically allows us to create interactive maps in R. I want you to install that MapView, uncommented, run it, comment it off again. And then finally, you want to install Viridi's. So if you remember, Viridi's is this color scale that is colorblind safe or colorblind friendly. We've been using it with ggplot already. We want to use it with MapView as well. So in MapView, we're going to call some functions from this package enable to use this color scale that is colorblind safe. All right, so after you've done all that, I don't know. I don't remember if I asked you to install tidyverse before. If you try to just run the library tidyverse, does that go through or does that, I mean, mine goes through and just gives me some messages, but it goes through. On your side, does it go through or does it say you don't have that package?
Works.
We installed it already.
Okay, so you have this already. Great. All right, so with that, you should be good to just remember to comment off or delete all the install functions here. And then once you have all that installed, you can just click the play button. This should go through without problems if you were able to successfully install all the packages. It gives you some messages here, but everything was installed. So I just want to take a quick moment here and ask if anyone had issue when you tried to load these packages, if you had any issues or any messages that were saying package not found or something like that. All right, I don't hear anything, so I'm going to assume everyone is good. We're going to keep moving.
Hello, Dr. Leo. Do
Yes,
we get to worry if we get like some warnings in red? Does it have any issue to do with the package?
So as long as it does not say error, if it says error, then you're probably something went wrong. If it says warning, I mean, sometimes warnings are just to let you know of certain behaviors of the package, but it doesn't keep it from actually running.
Okay.
Yeah. All right. Okay. So first thing, I want to remind you, we always do these, right? So we always first load our packages in the beginning of our script. And now the next step is importing data. That's always the sequence we're going to be following here. So we're going to import the data set that we wrangled last time. Let me close my email here. So I want to import that data set and assign it to this object called soyW, right? Now, I think maybe you've already been exposed enough to this that I can ask you, really ask anyone, if anyone wants to jump in and has the answer. So we want to import the data set we created last time. What function would you use here? What do you think, Aman? Okay, so Aman is saying to use read_CSV. Does that sound right? Anyone has any thoughts on it?
Yeah, it sounds right.
Sounds right, right? So one way that we would know this is basically if we go back to our, I think we exported that to data. So if we go to data, we should have a soybeans NASS process.csv. And because it is a CSV file, that's how you know which read function you should use, right? So let's go ahead and do that then. Come here on this chunk on soy W. Let's give it the assignment symbol and use read underscore CSV. If you remember, all we do here is just give the path to that file. So open and close quotation marks. Right now, you are inside of the code folder. We want to get outside of that folder. So we do // hit tab. Then we navigate to data, hit tab again, select soybeans NASS process.csv. This is the file that we all got from USDA NASS last time and wrangled, right? So it's not the raw version from USDA NASS, it's the wrangle version of that. So if you run it, you should see soy W on your environment, like I am here. And then we can print it below this chunk just to see, take a quick look at what that is, right? So if you remember, you should be seeing something like 5,897 rows of this data set, and then 4 columns. And those are year, county, production in bushels, and then production in million bushels. This is what you should all be seeing. All right, so if we just take a quick look here and remember that we have this column here called county, right? So we would imagine that there is somewhere in the internet, there's got to be a shapefile with all the polygons representing Georgia counties and their names. So we're going to use that information to connect our current data, which is not geospatial, to a geospatial format. If you come here on the next chunk, I left you a little bit of information there already. So I have there GA_CO, that stands for Georgia counties, just shortened for that. We're going to give the assignment symbol, and that USDA boundaries package that we just installed above has a function called US_counties. Well, I just typed US_ and then I left it to be auto-completed. So you can see there are like US cities, congressional, counties, states, zip codes. There's really a lot of things here that we can extract the spatial information of political boundaries. We're going to do counties because that's what we're interested in. But maybe you were doing a map for the whole US. You could use US states instead, right? So it's really up to what you need, but all these shapes are coming from that same package, USA boundaries. Here on US counties, if you just come in and hit tab, there's going to be a few arguments. We want to change the one called states. So we're just going to say states equals to Georgia. So if you run this, now we have an object called GA Georgia County. If we just print that, this is a simple feature collection with 159 features and 15 fields. It has a geometry type multi-polygon. It has a bounding box. It has a coordinate reference system that is WGS84. Remember, we talked about WGS84 in the lecture being one of the most common coordinate reference systems that you're going to see. And then it just shows the first 10 rows of this data set. So it has some different columns here where one of those columns is called, even though it's called name, but that column has the county name under it. So that's going to be key to us as we move forward. Before we move forward, I think this is perhaps the first time that you're seeing a spatial data in this class, at least. Maybe you've seen before, maybe you've seen outside of R, but in R, this is perhaps the first time. So I do want to just take a moment for us to understand how that looks like and what that is. If you run this class Georgia code here, it's going to tell you, if you remember, what is the object type? What is the class of this object? Notice that it is a data frame, but it's also an SF object. From the lecture that we had, we talked about some of the packages in R to handle both vector and raster geospatial data. The package we're going to be using to manipulate, to plot, to process vector data is going to be the package SF. And so this packet, this object here is of type SF already, right? So that is what we're going to be using in this class. If you remember from the lecture, so vector, well, let me just ask you all, maybe somebody in Tifton, since someone already helped me here. Can somebody give me an example of what is a vector geospatial object? Like, can you tell me an example in agriculture? What would be something that is in vector format?
Field boundary.
Okay, field boundary, right? That's of type boundary. Anyone else has any? Thanks, Polly. Anyone else has any other example here of a vector object that we use in agriculture?
Yield data.
Okay, yield data. Was that Marco?
Yes.
Yeah, that's right. So yield data, we have point type, right? So we have a point, many points across a field representing yield data. Great. So those are two great examples. So a polygon and a point. We also have lines as one example. And then in contrast to vector file types, we have raster file types, which are going to be more related to imagery, for example, right? Or maybe interpolated maps are also in raster sometimes. So that's just for us to have a quick refresher here that in R, we're going to be using SF to handle vector geospatial types. Like this one. So when I'm going to print again Georgia code so we can see again. It is a simple feature. It's how the package SF stands for simple feature. Collection with 159 features, which just means number of rows and then 15 columns. It will always have a geometry type. In this case, is multi-polygon because each row in this data set is one county and each county has its own polygon. So it's a multi-polygon because of that. We have a bounding box, which is just that box that would comprise all the data in this, that spatial box, that box in space that comprises all the data. And then we have this geodetic coordinate reference system, in this case, WGS 84. This is key because sometimes you may bring in a shapefile, for example, which is a vector type, a type of vector file that may not have a coordinate reference system at all. You have to set that first. So, and sometimes you want to change this coordinate reference system as well. So it's important to know what it is so you can change that if needed. All right, so I want to make a quick plot, a very easy plot here with this object that we just created, Georgia County. We're going to be using, so for static maps, most of the time, I will try to teach you with tidyverse packages. So you're probably thinking ggplot. If you're thinking that, you're right. So let's start with a ggplot call here. Let's leave that empty at this level and just add a plus and hit return. If you remember in ggplot, we need to specify the geometries that we want to bring in using the geom functions. SF objects have a special geom just for them that is called geom_SF. So here we're going to say data equals Georgia County. Oop, there we go. So this was my code. Let me just squeeze things here so we can see both code and output together on my screen. So we use geom_SF again because this object is an SF object. geom_SF is not going to work if you just have a data frame. It has to be an SF object, and then it just plotted that for us. Look how nice. So really we have all the counties in Georgia in this object, Georgia County. And really at this point, this Georgia County object has a lot of information coming from that USA boundaries package, right? So if you just printed, it has like a state FP, which is just a state code for Georgia. The county has a code as well. What else? It has the name of the county. It has the state name, which is all the same in this case. It has a land, a water. I think is the area of the state, or not of the state, is the area of the county that is covered by land and water in this case. So it has a whole bunch of information and then has one last column called geometry. So notice that up until from the first column until the last one, or maybe the one from last, so from state FP all the way to jurisdiction type, this is basically just a data frame. And then the last column is called geometry. And on this geometry column, that's where the actual spatial extent and coverage of each one of these polygons, that information is saved on this last column. So one of the reasons why in R, the package SF became so popular is because it was still very friendly as a data frame, and it had one column only that contained all the spatial information. If you ever use R before this class with geospatial data, you may have run into the package SP, which was the one that was used to be the most popular one before SF came out. And SP was really confusing because you had different parts of the object had the data frame, then a completely separate part of the object had the spatial data, and it was really hard to work with tidyverse functions. So SF made all that easier for us, and therefore always try to, if you're working with vector geospatial data in R, always try to use SF objects for that, because that's going to help you to manipulate and do analysis and all sorts of things. Okay, so we were able to now visually have a map of what Georgia County is. However, Georgia County does not have our data yet, or maybe our data doesn't have Georgia County's data yet, right? So we're going to have to join them at some point. So our goal next, on the next part of the script, is going to be to merge both our NASS data that we have in the object called SoyW with the Georgia County's geospatial data that are under Georgia County objects. And if you were thinking about it, yes, we're going to have to do some wrangling to get there. I left you some piece of code here. So we're basically starting with SoyW, our USDA NASS wrangle data. I'm having a couple of pipes here that I'm just showing you. So basically what this code is doing is taking SoyW. If you remember SoyW from last class, it had this category for other counties, right? This is an issue for us because now there's no boundary for other counties. We don't even know which counties are other counties, and that probably changes from year to year. So really makes no sense to try to connect the line other counties with a geospatial extent. We just don't even know what they are. So when we're joining these two data sets, we're going to be using that county name to be the connecting point between both of them. Our SoyW has these other counties or other combined counties values under that county column, as you remember from last class. So the first thing this code is doing is just removing all the rows from SoyW that are where county equals to other counties or other combined counties. So that's what's happening first. Okay, I just want to run that so you can see. Now we have, so SoyW has 5,897 rows. After removing those rows where county equals to other counties, we end up with 5,518. So we filtered out some of those rows for us. And now this column county only has the actual county names. We don't have more that other counties category. Now, I do want to tell you what's going on here in this next piece of code. Notice that on SoyW, we have our county column. It is all uppercase, the county names, right? On our Georgia County object, that's where all the geospatial information is. First, it has a column called name. So it's not called county, it's called name. And then all the county names are are title case, I guess, where the first word is uppercase and everything else is lowercase. This discrepancy here needs to be addressed before we can merge both these data sets. We have to have two columns. So in each data set, they have to have a column that is exactly the same as the other, right? So it has to match the column name. It has to match how the values of that column are written out. So we have to fix that before we can merge them. Going back to that chunk, I'm using here a function called str2title. This function here is coming from the string R package, which is very, very helpful to manipulate strings in R. So every time you want to do something with a string, for example, in this case, we're changing the title, we're changing the title case. But it could be that you wanted to remove something from that string, or maybe you wanted to only keep rows that had a certain pattern, or maybe remove between locations. So let's say you wanted to take the first to the 8th position of that string and just keep that. A whole lot of other examples. Every time you're messing with strings and you want to manipulate them in R, the package string R is what you need. So this function here, str to title, is coming from this string R package. If you just run it, I left you all the code already, so you don't have to worry much about coding. You just run it. And once you print, so the object that we are assigning all this is called soyw_all. Once you print that, notice that now our county values are all title case, right? So now, before they were all uppercase, now it's just the first letter uppercase and then everything else lowercase, which is exactly the way it is on that other object that we're trying to match, which is Georgia County, right? This is the one we're trying to match. Everything is title case in there. All right. I guess before I keep moving here, I just want to make some space to check if anyone has any questions about what we just did. All right. I don't hear anything, so let's keep going. So on the next chunk, now that we basically wrangled our soil_w object, especially related to removing those rows that don't have a geospatial county associated with them, and then changing the case of the county column to be title case. Now we're ready to merge that USDA NASS data with our geospatial data by using that common county name column. We're going to do that in this next chunk here. Or actually, sorry, we're not doing that quite yet. I'm jumping ahead. So we did a little bit of wrangling with our soyw object and assign all that wrangling to soyw_all. We're also going to do a very light wrangling with the Georgia County object and assign that wrangling to Georgia County W. And then both of them are going to be on the same position to be joined. So the Georgia County, let me just print Georgia County below here so we can take a look at it again. So a couple of things that we should fix, in my opinion at least. One of them is this object has 15 columns, 15 fields of information that for us, at least for this exercise, we really don't care about, right? All we want from this Georgia County is the county names and the polygon associated with them. That's all we want. I don't care about any of this extra information. So just to clean things up a little bit, we're going to do a select. Okay, so let's come here, do a Georgia_county. Let's use a pipe. I want to call select. If you remember, we're always making sure that this function is coming from dplyr. So dplyr : select. Now, which column names would you select here? If you just take a look at what's under here, if you print Georgia County, which column names would you select? Let me ask somebody in Tifton. Luke, what do you think?
If you said you just wanted the county name and the polygon, you could just do name and geometry, I think.
Perfect. That's exactly it. We can do that, and that's exactly part of my answer. I do want to show you something here that I don't remember if we saw yet in this class, which is to kind of do a rename of a column on the fly when you use select. So one potential issue we have here is even though we have the county names in the same format, but the county names on Georgia County are under this column called name, and they're under a column called county on the soyw. So that column name should also match across both of those data sets. So instead of just saying select name and category, I'm going to say county equals name. So county is the new name I'm giving. So I'm selecting name and renaming it to county on the same on the same place using the select function. So if you run that and you print it, we still have 159 features. It's saying we only have one field because it's not considering that geometry as a field because it's just the geospatial information. But basically now we have the county column which now is called county. We have all those county names, and then we have the geometry column. So at this point, we have both our soy W and our Georgia County talking to each other, right? Both of them have a column that is called county in both data sets, and all the county names are the same format in both data sets. So now we can do a join, which is going to be on the next chunk here. So I'm going to call this soy_sp. What we're going to do here is we're going to start off with Georgia County W, and we're going to do a left join. I don't think we talked about the concept of a left join yet, so I do want to take a little bit of a moment here to walk you through that. So what any type of join does is going to look for a common column name across two data sets, but not just column name, but also common values, right? Which in our case, we have that one column called county in both of the data sets. So that would be the column that will be used to connect these data sets. It's going to look at county, Tift County on the soy W, and it's going to look at the Tift County on the Georgia County object. It's going to merge them by that name. And so we're going to have one data frame that's going to have all the USDA NASS data with the geospatial data coming from Georgia County object. Because it is a left join, what it's doing is basically, if we start giving the Georgia County object, that is considered the one on the left. And then the one that comes after it is the one on the right. So it's going to go on the one to the left, and it's going to bring the data from the one to the right to match on it. This makes a difference sometimes if you do the opposite. If in this case we were to give the soy W first, that would be the left data set, and then bring in the Georgia County after that. It could cause changes here. So left join is a very, very useful function I use so many times. And I just wanted for you to be aware of why is it called left join? And if you see things going wrong as far as the number of rows you would expect, maybe if you change the order of which one is on the left, which one is on the right, that may fix it. But anyways, we're starting here with Georgia County W. Let's give it a pipe and call the function called left join. Inside of this function, we just give the soy_w_all, which is our object that we created above with the Wrangle version. If you run this, notice that it tells you that it's joining by the county column. It's telling us what column is being used for this join. And then if you print soy SP, which is what we're naming it. Okay, so notice what happened here. We have 5,488 features and 4 fields. If we look at the fields, we have county, we have year, production in bushels, and production million bushels, and that's it, right? So really now and then we have the geometry, which is also key here, right? So now we do have a geometry column here. So we have production in million bushels, which is coming from the USDA NASS data, with the county, with the year, also coming from USDA NASS, but now connected to a multi-polygon geometry. So now this is an SF object. We can plot it as a map. So that's really what we wanted to have here. One thing I want to quickly check is so soy SP has 4,488 rows. Soy W all has more rows than that actually. So it seems like maybe some rows were some rows from the soy W all were left behind in the process. We're not really gonna look into that right now. I think it's gonna be easier for us to make some maps and try to discover what happened. But I just wanted to tell you that one good way for you to check if you're left, especially if you have a lot of data like this, that is difficult to just look at the data set and make sense. One way to check if your left join was done correctly is by checking the number of rows you were expecting to have at the end. So really, I wanted to have soy W all. I was expecting to have all these number of rows back on soy SP. We have fewer than that, and I'm not fully sure why, but it's just a way that we could use to check here if that join was done properly. All right, so the first thing we want to do here is do a static map. I want to show you how to do a static map, and specifically of the year 2023. So if you come here on the next chunk, so if I'm telling you that I want to do specifically on 2023, what would come to your mind as the next step that we need to do here? Filter, right? Yeah, so let's add a pipe here, do a filter. If I print soy SP just so we can inspect what it has, so it has that year column, right? So we can just say year equals double equal sign. Remember, this is a Boolean operation, 2023. And then if we just print this or run this, we get 19 rows of data. So basically in 2023, there were 19 counties in Georgia that reported soybean production. All right, so after that, we can get right into our plotting function. I want to give here that the pipe, and then we're going to call ggplot as always. We can leave the ggplot information at that level empty for now. We're going to call some geom SFs next. So let's give it a plus. Remember that we use the pipes everywhere else except inside ggplot. Inside ggplot, we also always use the plus sign. So the first thing I want to do here is call geom_sf, because now notice that our soy our soy SP object, which was combining the USDA one with the Georgia County one, is an SF object, and therefore we need to use a geom SF to plot it. So we're going to say data equals, where is it here? Well, soy SP. Right, so data equals soy SP. If you just run that, this is what we see. Or actually, I don't think we need to say data, sorry, because the data is coming from the pipe above. So maybe if we just run it, yeah, we don't need to specify data. So if we just allow it to run like that, we see here that these are the 19 counties in Georgia that had soybean production reported in 2023. So let me ask you this. If I wanted to have these counties colored according to production in million bushels, what would you change in this code? We have not done that specifically, but I think you've been exposed to the concept in other forms that you could get to that. What would you do if we wanted to color these counties according to production?
We do scale color.
Yes,
Scale color.
scale
Scale
color.
color.
So like after the GMSF? Okay, so we could do scale, color, and then what? What do you propose we do here?
Production in million bushels.
Well, are you seeing my?
No, we do county, but
Where? Do you remember? So we could at some point use the scale color function, but I don't think we're at that point yet. But you're thinking right. I guess you just perhaps you were missing the place of where that would go. Can someone else help Kiati here? Where would you do that? Let's see. Benedetta, do you have any thoughts?
No, I have no clue.
No, no problem. Let's see, Mohit. Is Mohit there? I cannot fully see.
Oh, it's not here.
Okay, do you have any thoughts on what we could do here?
Could you do an AES function and set color equal to your bushels? Is that what you wanted to map it by?
Yes, is that Luke?
Yes.
Yes, that's right. Thanks, Luke. Yeah, so remember that every time you want to change an aesthetics of the map or the plot, according to a column, it has to go inside AES, right? That's the key here. So GeoMSF also has an AES function. So we're going to come here and call AES. And then here we can say, in this case, we want to change the aesthetics for fill. So we want to do fill equals to, and then if I just print here soy P just to see again, is going to be prod million bushels, production million bushels, right? So this is what we would like to have. Awesome. Kathy, I think you were getting toward to this step, but maybe you didn't realize that it should go on the AES function, but you were getting there, you were in the right path. So yeah, so now we can see the production in million bushels of the 13 or 19 counties in Georgia that reported data in 2023. All right, this is, it's useful, I guess. It's interesting to look at it. But it's not very spatially informative, right? Because we only filter the counties that had data in 2023, then we're basically missing all the other counties that did not have data in 2023. So what would you do in this case? How can we solve that if I wanted to show all the counties and then the counties that had data in 2023, like we are here? So one concept that I think you maybe you're still in the early phases of learning that is that ggplot is incremental. And the order that you specify things makes a difference. So for example, do we have an object that has all Georgia counties that I could have on the background and then bring in the 2023 data on top of it so I could see all the counties together?
Yes.
We do, right?
Yeah.
So we have we have that Georgia County W as one of those objects. So let's go ahead and do this. Oh, sorry. Was somebody in Tifton say something?
I was going to say if we want the map for the entire county, we can move the year option, not specifying the year, so we can get the map for the whole county.
So we can try that and see what happens. So if I just comment off the filter of the year and then just do the plotting. So this is what happens. If you go back to the data set, we have data since like 1969. And because all that data is there, we're not telling it to change how the year is being handled. It's just plotting all years on top of each other. So it doesn't really help us with the visualization of the data set. Although now we do see at least all the counties that had data at least one time during that period. It seems like some counties here never had data, which is where you see like the gray shapes here. It seems like those counties never had soybean production reported with USDA. So what I want to propose to do here is to keep our filter because we do want to show data for 2023, but then bring the layer that we have, the data set that we have that has all Georgia counties. So let's give it a plus here. That object, I mean, we have a few of them, but we can use the Georgia County W. If you remember, that was the wrangled version that coming from the USA boundaries package. That is an SF object, and because of that, we have to use GeoMSF. So because now it's a different data set, we cannot just, we have to specify the data set name and not just let the one coming through the pipe to represent it like it was on the first GeoMSF. So we're gonna say data equals to Georgia County W. And let's just run that to see what happens. Okay, so what is going on here? I mean, I still have the same legend as before, but I don't have the data anymore. What is going on? So one key sentence I said maybe a moment ago is that ggplot is sequential. So it adds layers as you are providing them.
Yeah.
So what's happening here is that Georgia County W is coming on top of our 2023 data. So it's basically hiding everything else behind it. There are a couple of ways we could fix this. One of them, it would be to come here on Georgia County W and changing the fill, because right now it has a gray fill, that's the default. We can change the fill to nothing, which would just be fill equals NA. Let's see if this fixes. All right, this fixed it. So now basically the fill of the Georgia County layer is fully transparent, so we can see through it. We can see what's behind it. This was one way that we could fix this, but there is another way we could also have done here. So if I did not want to change the fill to NA of this layer, so just going to go back to what it was before. Another thing we could have changed it is use the fact that ggplot is sequential and just move this line of code to appear first. So first we're plotting Georgia County, add a plus there, make sure we remove the plus on the last line of code here so it doesn't interfere. So now it's first plotting Georgia, and then on top of that is plotting our production of 2023. This would also work, and it did not remove the fill of the Georgia County object. Awesome. All right, any questions about this? Okay, I don't hear any, so I'm gonna move forward a little bit here. So my next goal is to show you, or maybe to talk to you about some of the ways that we could do to make this plot more professional, right? I mean, right now it's a nice plot, but we could improve it a lot. So what I am doing here on this next chunk, I left you the code that basically pretty similar to what we developed above. The only difference being that I'm changing the size to 0.2, which basically just changes the width of the polygons here for the counties. So if you just run what I left you here on this chunk, and you look at the output of that, it's just changing the width of the line. I mean, to tell the truth, I think it's very similar, but maybe when I made this, it was a different version of package that it was more different. But anyways, if you want to change the width of the line, so maybe let's put 1 here, just so you, so instead of 0.2, just change that size to 1. It actually did not change. Maybe this has been a difference in an update of the package. Maybe this is called line width. Let me try that. See if that makes sense. Yeah, so I think there was probably an update on the package that changed the argument name from size to line width. That's what was going on there. So line width is what it would change, what it would specify to change the thickness of the polygons. I want to do 0.2 again and keep line width. Yeah, so now I think it's a little bit of a finer stroke as the original version. All right, so here's the list of things I want to change on this plot to make it more professional looking. So I want to select a colorblind safe palette, which is what Kathy was mentioning earlier. I want to change the fill legend label. So right now the fill legend label is prod mibu, which is the name of the column. I want to change that. I want to add on this map the county names. So I want to have the names of those counties listed on the map, and then change it to a theme, to a ggplot theme that's a little bit more clear. So starting with this code here that I left you, what we're gonna do is add a plus right at the end. And then I want you to come right below each comment so you keep tabs with what we're doing. All right, so first thing is I want to select a colorblind safe color scale. How do we do that? Who can help me with that? Okay, so Aman is saying scale underscore fill, and then
Viridis.
Viridies, right? Yes. So if you remember, we have here a few different options for Viridies. Maybe we can use, let's see, maybe we can use the option for C. So C is for continuous. Let's use that first. I want us to play a little bit with that so you get some understanding of the difference. So this is what it looked like. We're seeing, I mean, it is that Viridis scale that we're used to, and it is continuous, right? Even though we have these breakpoints, 0.1, 0.2, and so on, it is continuous. It doesn't look as continuous on the map, mostly because we just have one full value for each county, and we only have 19 counties, I think, or 13. So we really don't have a lot of values, but this is a continuous scale. Sometimes you may want to make a continuous scale to be binned. You may want to make bins of values and assign the same color to values inside a given bin. We could change this to Viridis B, and that B stands for binned. So if you run that, you'd notice on the legend now there are bins, right? It's not like a continuous legend anymore, even though, again, the plot didn't change as much because we only have a few values, but now the scale is binned. All right, I do want to show you here something that I don't think we explored yet. So Viridis, the default Viridis scale is this one from like dark purple to a light yellow, but there are other color scales inside of Viridis that are also colorblind safe and just give a little bit of a difference. So if you come here inside of the scale field Viridis, there is an argument for option. Sorry, there's an argument called option. And if you ask for help of this function, scale field Viridis, you would see all the options available and what they mean. I'm not going to do that. You know how to do, you already learned how to do that yourself if you're interested. So you can do that on your site if you wish. But basically there are options that go all the way from A to G, I think, and they're all uppercase. So let's try option uppercase A, see what that is. So I think this is magma perhaps, or something like that. It has a specific name. And then if you try B, it's going to be yet another one. It's similar but different from A. And then all the way, I think that the default Viridis is probably D, I believe. That's the option. But you can play on your side. Yeah, so D is the default Viridis. But there's a lot of them here, and they're all colorblind safe. So if you're trying to do plots, maps, colorblind safe, and you want to add some variety to your color scales, not just always be that Viridis traditional one, you can do that for changing these options. All right, I'm gonna go back to the original D scale, D option. That is the typical Viridis just for now. So we can keep moving here on our customization of this map. All right, I'm gonna add a plus at the end of the line, go under the next comment where I want to change the fill legend label and also give a title to this plot. What function do we need for that? Let me look for somebody in Tifton. Can anyone remember the function we used before when we're trying to change the legend labels?
Labs.
Yes,
Lab.
labs, that's right. Thanks, Polly. So the function labs here if you just type that out and you hit tab, it's going to give you a lot of options here of what you can change. I want to change, and even some things that are not listed here. So we can say X, Y, color, fill, anything like that that we're changing on the map. So I want to change here our fill, right? Because we're assigning fill to production in million bushels. So on the labs, I need to say that I want to change the legend of fill. I want to call this, so give it quotation marks, production, and then in parentheses, million BU for bushels. Let's run that and see how it looks like. So we changed to this long name. And right now, I think this title is kind of too long. I wish I could break line here and have million bushels under production. An easy way to do that in a string, which production million bushels is a string, is you come where you want to give a break and just type /n. When R interprets this, it basically knows that /n means a break of line. So it just broke the line for us right there. All right, the next thing I want to do here is give this map a title. So here on the labs function, there is if you just give a comma, there is also an argument for title. I want to call this county level soybeans production in 2023. That's the title I want to give it. And so now I want to just run it, and then we have a title on our map. All right, next thing I want to do here is add county names. So if we check our object that we're working with, which is this incoming object of the soy SP that was filtered to only contain 2023, if I just print that, so we remember, we have a column that says county. So I basically want to take this text here and make it appear in each one of the counties that it represents. So we're going to come here after the labs, add a plus, come after that comment of adding county names. Because this is an SF object that we're working with, it has a function called geom_sf_ either label or text. The difference between them is that text is just the text itself, and label is a text with a background around it that looks like a label. So I want to use text for now. Just specify that we want to use the data frame that is coming through the pipe, which is soyp filter 2023. We're going to say data equals to tilde dot. So this is basically telling R to put that data frame that is coming through the pipe right here again. All right, let me ask you this again. Let's see how you're thinking here. If I want to assign a label to each county in 2023, how do you think we'll do that? I mean, you haven't done this, so I wouldn't fully expect you to know the answer, but maybe if you can just give me what you're thinking in generally. It's going to be on this function, geom_sf text. Do you think it would be inside of AES function or outside? So we're gonna give the text that we want to use as a label in this function. So not the color. I mean, it could be the color too, but specifically we're going to be the label. Inside AES. So Amandeep here in Athens is not quite sure. Anyone in Tifton perhaps has any thoughts? Kiathi, what do you think?
I think we should use it inside AES, but I'm not sure.
Okay, so why do you think it should go inside AES?
Because all the details we have given to the plot we have given inside AES, and this goes inside the plot, right? Inside each county.
Yes, yes, that's the key of the thinking. All right, so we are trying to assign something about about our data in this case, which is going to be a different label for each county, and map that to a column that's called county. So because we have this word of like, I want to map something to a column, I want to map the label of this text to the column county, that should go in AES, right? If I wanted to give a fixed label for everything, maybe go dogs, then it would not have to be under AES because everything would get the same label, right? So because we're mapping the labels to a column, it has to be under AES. And then in this function, geomsf text, it has a special AES option that is called label. So we say label equals to the county, the column that is called county, right? So we have a column called county that has all the county names. That's why we're specifying county. So if we just go ahead and run that, this is how it looks like. So we basically took each county and whatever name it was under the county name, the county column, that's the name that it added. That's the text that it added to the plot. Now, this is kind of too big, right? We want to make this a little bit smaller, perhaps. These county names are too big right now. So I want to come here on the geom SF text. Outside of the AES, I want to say size equals to 2. Let's try that. Okay, so now the names are a little bit more manageable. And notice that we have some counties, most of the counties are actually have like a dark background, right? Like a dark purple. So perhaps it would be easier if we had the labels that we added here with a different color rather than black. So let's come here on the geom text. We're going to change the color to white. Okay, maybe helped a little bit. You know, just to kind of make this connection again. If you're changing the size of everything, if you're changing the color of everything, if you're changing anything about everything, it goes outside AES. It goes inside AES if you're changing values of something according to a column. Every time, for geom or not, any geom. Okay, so it's getting, getting closer to what I was anticipating. So the one next thing I want to do here is change this map theme to something a little bit more clean. So let's come here at a plus. If you remember, there are many theme options that we could choose. I want to choose the theme called theme_void, which is basically an empty theme for us. So this is the name of the theme. Let me squeeze so you can see the function and the output. Okay, this is looking nice, right? It's looking a lot better than our initial attempt, which was this. Right? So it's looking pretty good right now. So the next thing I want to show you is an interactive way of making a map in R. So a lot of the times when I'm teaching R, especially precision ag in R, one feedback I got in the past was everything was so static. Like if you work with geospatial data in like ArcGIS or QGIS, interactivity is right in front of you the whole time, right? In R, that's not the case. So I do want to show you a way that we can make our geospatial layers interactive in R. So if you come to the next chunk here, what I'm doing is I want to first extract just 2023 and then assign that to an object. I was actually calling SoySP22 because last year, the last data we have was 2022. You can just change the name of the object to SoySP23. If you run this piece of code and just print SoySP23, it is basically the same data set we were working above here, where it's just data from 2023. Nothing different. It's just that now we assign that to an object that we can call in a function. So that's all we're doing here. Oh, actually, before I show the interactive map, I think I forgot to do something here on the previous chunk. So I forgot to export this plot to file. So let's do that here. What function do we use that for that again? Okay, so Aman said something here I don't want to say because I want to hear if somebody else also can help me. What was the function we used to export a plot, a static plot?
Is it ggSave?
Yes, that's right. Thanks, Kathy. Yeah, so both Aman and Kathy mentioned ggSave. That's right. So we're gonna just call ggSave on that chunk where we created that plot, the static plot. Give it the quotation marks. We're gonna get outside of the code folder, // We're gonna go inside the output folder for the first time, I think. So now we're exporting, we're outputting something from our analysis that should go on the output folder. And then we're gonna give it a name. I just wanna call this soy-prod-23.png. So notice that here we give the path, the file name, and the file extension all on the same thing, all on the same string. If you go ahead and run that, and then you go to your output folder, navigate that on your files tab, click on that soy-prod-23. This is how that looks like. So here actually it looks pretty nice, right? I mean, it was saved as a 7 by 7 inches image. You could play around with that. You can make it smaller, bigger. And every time, I don't know if I think I said this already, but I will remind you every time that when you are trying to create a plot and you're trying to find out, okay, should I make this taller or shorter or wider, whatever it is, you don't want to make that decision just by looking at the output below the chunk, because the output below the chunk is going to fit your screen. So as you move things around, is that the way that looks like on your chunk is going to change. However, once you export a file and you go on output and look at that file, this is how it will look like if you bring this figure into a poster or representation. So let's say, one way for us to increase the font size here is to decrease the size of the plots that we're exporting. So the default was 7 by 7. That's what it did. But if I wanted to change the width and the height of this plot to maybe something else, maybe 5 by 5. So width equals 5, height equals 5. I run that again. It re-exports in 5 by 5 dimensions. And if I check on it, look how the text looks bigger now. And that's just a function of you exporting as a shorter, smaller file size. Then the text comes out a little bit better. Awesome. All right. So now we have a very nice map of Georgia counties with soybean productions in 2023. We could include this in a poster or anywhere you would like to show that type of information if you wish. Okay, so our next step here is going back to that interactive map of Georgia soybean production in 2023. We created that object, soysp23, to contain only that data. We're going to call the function that is named mapView. So mapView is a function that's going to help us to do interactivity with maps in R. So what I want to show here first is that soy_sp_23, and just run that just to see what happens. So this is the output we get. If you play around, this is an interactive map. You can zoom in, zoom out, you can click on the polygons. All the data associated with that polygon pops up. You can, really zoom out as much as you want, zoom in as much as you want, and play around with it. Something that I think is useful is, so this base map is the map that is showing behind. So we did not ask for this map of the world to show up. It just showed up by default. And there are some different base maps that we can have access to on MapView. If you come here on the hamburger menu here, the option that was selected by default was CartoDB Positron. you can play around with any of these options here to see how that would impact. So Carto, DB, dark matter, OpenStreet, as real world imagery. This would be your satellite imagery background is as real world imagery. You can really zoom in and actually see more than just, like streets or things like that. Can really zoom in and see fields, right? And then last, I think there's one more perhaps that I skipped. Let me see. And then open topographic map. Those are the options that we have here on map view. Okay, so maybe let's keep Carto DB positron as our default since it came like that. So map view is not ggplots, right? So we were talking a lot about ggplots. Every time we make static maps and plots is gonna be through ggplots. Map view is a different thing. Remember that one of the reasons why I am teaching ggplot2 is because it follows a similar philosophy of how to specify things and how to work with things as throughout ggplot, but also across other packages of the tidyverse. This is why. This is basically why. Now we're using map view, which comes from a different package that is not tidyverse. And the way we specify things is going to be completely different. And this used to be the default in R. Every single package you use, there would be a different way of specifying the same thing. It gets tiring because you need to learn basically how to specify the same thing across different packages. And so tidyverse came to fix that. There is not an interactive map option within the tidyverse, so we're gonna have to stick with map view, but I do want you to appreciate that difference there. Now here on map view, if I do want to map, so let's say I still want to have this map interactive, but I do want to have the production, I want to have the counties colored according to their production. On ggplot, it would be inside AES. Map view does not have that concept. So the way the map view works is if you give it a comma, it's going to have many arguments really. We're going to change a few of them. For us to change what column is used to color different polygons, there is an argument called zcol. That means the color of the variable z, I suppose. So here is where we give the column that we want to color by. So that is prod underscore million bushels. If you run that, now we get those counties colored by the column. We see that the default color scale that MapView uses is already Viridi's, so that's pretty cool. We don't have to worry much about that in there. If you see these counties, they have a little bit of a transparency, or these polygons have transparency. You can see through it, which can be a good thing, can be a bad thing. But if I wanted to make them fully solid, so no transparency at all, I want to show you how we would do that. So you come here after that zcol, give it a comma, break line. There's an argument called alpha.regions. And we are going to set that equals to 1. So alpha is normally the way that we refer to transparency. And it normally ranges from 0 to 1, where 0 is fully transparent, 1 is fully solid. This is how we would have it fully solid. If we wanted to give it back some of the transparency, it just changes number to something less than 1 and greater than 0. So let's say 0.1. So that's how it will look like. I think I'm okay with maybe a 0.8, like 80% solid. I think that's fine with me. And now the next step I want to show you is if we want to change the color scale being used here. So we were in ggplots, we were changing that by using the function scale underscore fill underscore Viridi's. MapView does not follow the same. So we're basically going to use a different argument that for MapView is called whole.regions. So is the color of the regions, where regions are whatever you're mapping. And we're going to use a function here from the Viridi's package that we used before. So Viridi's has many different color scales. One of them is called plasma. So if you, and this function again is coming from the Viridis package. And let's say we want plasma with 20 color values in that color space. I just say plasma 20. So if I simply just run plasma 20 here, what that does is it takes this plasma color scale and gives me 20 values of colors identified by their hex code. We talked about hex codes before as well. If I just wanted 10 values, I just change to 10. Right, so this is basically how that works. And then we're just giving this string of color values to this argument call regions. That's all that's happening here. So if we run all that, this is what we get. We get the map with our soybean production with a color scale that is based on the plasma color scale, also colorblind safe. All right, so another thing that I want to do next here is I still want to show all the Georgia counties here. But as we've seen with ggplot, by only bringing the layer that has data from 2023, that does not happen. So what we're going to do, which is a concept perhaps the map view borrowed from ggplot, is that you can add a plus at the end of the line, hit return, and call another map view. It's almost like calling a different geom in ggplot, but calling another map view map. What I want to bring here is the object that has all the Georgia counties. So that is the Georgia underscore CO underscore W. If we just run that, this is what we get. Notice that it already chooses one of the columns and colors the counties according to that column. That's a default in map view. That is not a default in ggplot. So we need to basically inhibit that. One way of doing it is we can come here on this map view, give it a comma. We can say col.regions and then just give it one color. We can just give the color to all those counties as white. And that basically fixes that issue. You can also notice that that these counties, all the Georgia counties, they came afterwards. So that concept of being on top is being applied here. So one solution is to change the transparency. So let's give it a comma. I want to call alpha.regions equals to 0.1. So we can see better the soy SP23 that right now is behind the Georgia county. Something else I want to do here is if you notice, so this window here, you can open that up as a separate window so we have more space. So Georgia County object has 159 counties, and it just gave us a very non-friendly legend with all the name of those counties on the side. I really don't care for this legend, for this Georgia County W legend, because it's all the name of all counties. I don't really need that. So I want to basically inhibit the legend of that second layer. To do that, we can come here and we can basically say legend is another argument here equals to null, and null needs to be uppercase. If we run that now, that legend specifically to Georgia County W is gone. We just have the legend for the production, which is what we really care about. And then lastly, I want to show you one more thing we can change here, and that's going to be it. There are many things we can change, but I'm just showing you some of the ones I think are most relevant. So let's say that we are going to be working in our next class with open source data for a field that you may bring into class. It may be the field where you do research. It may be perhaps the field where you have your farming operation. Whatever field, as long as it is an ag field, you can bring that into class, and we're going to pull open source data for that. So whenever we do that, we want to have the Esri world imagery as our base map, as that's going to be more helpful for us when working at a field level. Although we have the chance of selecting that within map view, but the default, every time we make a map view call, is going to be CartoDB positron. That's the default. It's always going to come that. if we want to change the default base map to be Esri world imagery, we can do that on an argument. So if you come here on the Georgia code W, let's give it a comma. It has an argument called map.types. You can say equals to, and then you need to give the value that matches that layer. The value that we are looking for is this, esri.world imagery. It has to be spelled exactly like this. So uppercase E, uppercase W, uppercase I, with a dot between esri and world imagery. So let's try that. If we come here on map types, esri.world imagery with E, W, and I uppercase. If we run that, well, it did not work. For some reason. Let me see, what am I missing here? Maybe I misspelled something. esri.world imagery. I don't see if I made a mistake. Maybe we have to specify this on both layers. Let's try that. Both the soy SP23 and the Georgia County. Yeah, so maybe that's what it was. You have to, maybe the one you specify on the first map view layer is the one that counts for the remaining ones. But that's how you would do it. And then this way, every time you create this map, is going to come with that world imagery as the background base map. All right, we're getting to the end of this class. I want to show you two more things, and then I'll open for questions. One is, one very cool thing about creating reports from Quarto. If you want to go ahead and click on the render button, again, if you did not have any errors in your previous chunks, it should render correctly, everything correctly. If you had any chunk that had an error, that chunk would not render correctly. So just so you're aware of it. So now that it rendered, I'm gonna pop this up on my, oh, let me do that again. Maybe I did it too fast. So once it rendered here on our studio on the viewer pane, I just clicked on this button to open on my browser. And then just like before, we have the code, we have the output and all that. We're gonna have our maps, our two static maps. So the not so professional one, the professional looking one. And then we have our interactive map being interactive in this HTML, which is super cool. In this case here, 2023 data for soybeans production in Georgia is not that exciting of a data set. There's not a lot of data behind it. But I hope you can think of ways that if you're working with geospatial data, you want to give your collaborator, maybe your advisor, the chance to play with the data a little bit, even if it's just on a map to zoom in, zoom out. You know, if you click on the counties, it gives you all the data for that county in this data set. You know, if you want to provide them a report that also allows them to play a little bit with the data, you can do that through HTML reports, and it's really fun. I've taken this to a different level on my research, so I'm not going to be fully teaching you this in class, but just to give an idea, let me launch something here to show you. So I developed a dashboard that basically takes cotton variety trial data from Georgia and displays that data in maps, and so this is data that our cotton specialist Kemp Hand runs the trials, collects data. I basically just got the data from him and did a dashboard where you can interact. So here we're looking at lint yield from 2021 data. I can look into different cotton quality parameters collected on those trials. We have a comparison of all the trials here from worst to best, and then precipitation and maximum temperature during the growing season for each one of the trials. So you can either select what variable you want to look into, which changes all the maps, or which county you want to focus on, which changes the weather one. So just another way for you to think of ways you can use Quarto files to create fully interactive dashboards for others to use that include even spatial data in this case. All right, let's see. Let's go back here. Okay, so this basically wraps up this exercise. We're not gonna have time to talk about the mini project today. We'll do that on Thursday, so that's gonna be the first thing I'll introduce is the mini project, share with you the instructions and how that's gonna work. And so just a quick summary of this exercise here today. We basically learned how to connect tabular data, the one we got from USDA NASS, with geospatial data. As in this case, as it related to county level type of data. This could have been to perhaps state data if you have, let's say you do a survey and you want to connect that to different states that responded. You could do the same thing. So we connected tabular with spatial data, and then we created a publication-ready static map and an interactive map as well. And also we took a look into how to develop these rendered high-quality reports that you can share. So you're developing your analysis, you're doing everything on your side, and if you are paying attention to a few details, you can easily extend that to be a very sharp, professional-looking report you can share with anyone. We looked into HTML. It could have been PDF. It could have been Word. It could have been different things. All right. Any questions?
So, I got a problem in the last part because when I add the RC word imaginary, it turned out all gray.
Okay. So did you try to include that in both of the map views?
Yes.
Okay. Maybe can you double check your spelling because it has to be exactly right?
Already it was right.
Huh.
Check about the alpha region if you set .1.
So, yeah, I said it as well.
So Benedetta, what you can try as well is just try running. So if you have your cursor anywhere in these lines and you run, it's gonna run all of this. But what I want to ask you is if you just select this map view that has your Georgia County and just run that by itself, so not connecting with the SoySP23, see if that works.
No.
No. Interesting. Yeah, I'm not sure. If you maybe can you send that question on GitHub on our issues, and maybe we can take a look at the code and see what's going on. Does it give you any warning or message?
It runs the map, but in the map there is nothing. That's the only thing.
Okay. Well, if you can start that question on GitHub, then we can try to help you there. If we cannot figure out on the code, maybe Neva can try to connect with you and see what's going on. Because this feature, well, were you getting the other base map?
What you mean? Like before adding the RC word type imaginary, it was all normal. Just adding that.
Okay. So if you were still seeing before, then that's the important thing. But we can try to figure out why it's not changing the default for you. Yeah, if you can take a snapshot of your code and paste that on GitHub on issues, you can open an issue and then we can look into that. You know, I just noticed, sorry, I think we're 5 minutes over. I apologize for that. The computer right in front of me is showing me 4:01, but then I looked at my computer and I saw that we're at 4:05. So let me wrap things up here by getting your attendance. So 2025 PPA. I'm going to open an issue here for your attendance. So attendance January 28. Please claim your attendance, and after that, you're good to go. I have to run as well for another meeting, so unfortunately, I'm going to be able to stay for questions if anyone has. But please use GitHub issues if you have other questions, and then I'll follow up with you on there. Make sure you claim your attendance, and then you're good to go. So I'll see you all on Thursday.
Thank you. Thank you. See you.